Hello everyone, my name is Róbert Várdai. I would like to talk about the improvement of the impact resistance of three-component hybrid PP composites with polymeric fibers. For structural and automotive applications, the impact resistance, stiffness, and strength of composite parts are crucial factors. The required large stiffness and strength is usually achieved by fiber reinforcement. One of the most important goals of composite development is to increase the impact resistance and stiffness at the same time, or at least improve one without sacrificing the other. The combination of stiffness 2, 4 gigapascal and impact resistance larger than 15 kilojoule per square meter is often the targeted property profile of the materials used in automotive industry. Glass and carbon fiber reinforced polymers have been used for decades, but increasing environmental awareness and also some economical aspects created much interest for natural fiber reinforcements. So natural fibers are not as stiff, of course, and strong as glass or carbon, but they have considerable advantages, including their natural origin, environmental benefits, small density, and low price. So the proper selection of the matrix polymer, the fiber, and the composition may lead to the required strength and stiffness for most applications. The properties of all heterogeneous polymers are determined by the same four factors: component properties, composition, structure, and interfacial adhesion. All four are equally important in determining composite properties. In order to achieve optimum performance and economics, these factors must be optimized. Under the effect of external load, heterogeneities induce strength concentration. Micromechanical deformation processes may occur in the composites prepared. These processes can be energy absorbing mechanisms, which are very important in the improving of impact resistance. The aim of this study was to determine the effect of polymeric fibers on impact resistance of three-component hybrid PP materials and the identification of deformation and failure mechanism occurring during deformation. Impact resistance is usually increased by the addition of elastomers. However, this method of the modification decreases the stiffness of the material to below 1 gigapascal at large elastomer content, which is not accepted in many applications. It is clearly visible in the figure that the impact resistance is decreasing as a function of stiffness by increasing elastomer content in the case of wood floor reinforced composites. On the other hand, the fiber modification usually results in the simultaneous increase of stiffness and strength. Another important thing is the advantageous properties of polymer fibers. So these fibers are flexible, they do not fracture during the processing, but during the failure, these fibers absorb much energy by the occurring micromechanical deformation processes, which result in increased impact resistance. Polypropylene hybrid composites were prepared by the combination of traditional reinforcement, wood, glass, carbon, and talc, and polyvinyl alcohol, PVA fibers. Impact resistance is improved because the presence of these flexible polymeric fibers increases the number of potential energy absorbing mechanisms in the composites. Interfacial adhesion was regulated with the use of maleic PP. This is the MAPP. The composites contained 20% weight percent of traditional reinforcement, and the amount of PVE fiber changed from 0 to 40 weight percent in them. The most important characteristics of the reinforcing fibers are collected in table below. The components, the fiber and the matrix polymer were homogenized in twin screw compounder. PVA fibers were dried before extrusion at 80 Celsius degree for 4 hours in a vacuum oven. Extrusion was repeated once in order to increase the homogeneity. The granulated composites were injection molded into standard tensile bars. The specimens were stored at ambient temperature for 1 week before further testing. The mechanical properties of the composites were characterized by tensile and impact testing. The structure of the composites and deformation mechanism were studied by scanning electron microscopy, by recording micrographs on fracture surface created during tensile and fracture testing, respectively, and acoustic emission measurements as well. Yes. So this slide shows the results of stiffness of the composite. On the left side, you can see the results of traditional composites, while on the right side, the results of the hybrid composites. Composites prepared without coupling agent is marked empty symbols, while full symbols indicate the addition of the coupling agent. In the case of traditional composites, the stiffness increases significantly with increasing filler content. The carbon fiber increasing the stiffness in the greatest extent, while talc can increase the stiffness to a similar extent as the glass fiber. So we can conclude that the extent of the reinforcement depends on the modulus of the components as well, on their volume fraction in the composite. In the case of hybrid composites, right side, the stiffness increases slightly with the PVA fiber content, except in the case of carbon fiber composites, where the debonding of the polymer fibers is assumed even in small deformations. Furthermore, it can be seen in the figure that effect of the coupling agent is negligible. On this slide, you can see the results of strengths of the composite, as can be seen for both traditional and hybrid composites. A much larger strength can be achieved by using the coupling agent. The glass fiber has the largest reinforcement effect. In the case of hybrid composites, it's worth to draw in the attention that the talc PVE composites with the blue symbols have similar strengths, and the high performance carbon fiber reinforced hybrid composites with the black symbols. On this slide, I present results of impact tests of the composites. The figure on the left shows that reinforcement with larger aspect ratio provide larger impact resistance. In the figure on the right, the broken line shows the maximum impact resistance value achieved by the traditional two components composites. So it can be seen that much larger impact resistance can be achieved even with the use of only 15% PVA fiber. The largest impact resistance was achieved without the use of coupling agent in the case of glass fiber reinforced hybrid composites, which was 30 kilojoule per square meter. This value is already very favorable for the industry. It's worth again drawing the attention on the fact that talc PVA composites has a similar impact resistance as carbon fiber reinforced PVA hybrid composites. It is important because the price of the fillers is very different. Okay, Instrumental fracture was instrumental fracture test was also performed on the composites prepared. In this way, we can determine not only the energy absorbed during the fracture, but also the nature of the fracture. The figure on the left shows the force time curves of two-component composites containing different amounts of torque. As the amount of torque increases, the force required to initiate cracking also increases. The area under the curve is related to the amount of energy absorbed during the failure. The area under the curve is yes. When the maximum force is reached, the crack passes rapidly through the cross-section of the specimen. The nature of the fracture in this case is brittle. In the case of hybrid composite, as the PVA fiber content increases, the force required to initiate the crack increases. The crack does not move momentarily, and the flexible polymer fibers hinder the rapid propagation of the crack. The nature of the fracture is tough, even at low PVA fiber content. In parallel with the tensile test, we also performed acoustic emission measurements. On the slide, the stress versus strain curves and the cumulative number of signal strains are visible. Each blue symbol indicate individual events that occur during deformation, the source of each signal being some kind of micromechanical deformation process. The location and distribution of the symbols on the figure include a lot of information, and it is difficult to interpret. So we created a cumulative number of signals. This is the black solid line in the figure, which sums up the number of individual events up to a given deformation. The shape of the curves and the number of signals can provide information about what was the domination deformation process. In the case of carbon fiber composite, the process takes place at small deformation. This process is the fracture and the pull out of the fibers. The number of signals is around 20,000. Negligible amount of signal is detected in the torque reinforced composites due to the fact that the small particles don't give a signal which can be detected by acoustic emission method during the bonding. On the next slide, I will present the acoustic results of the hybrid composite of the composition shown here. Yes, so for hybrid composites, a much larger number of signals was detected because of the PVA fibers. In the case of carbon fiber PVE hybrid composites, two different processes can be defined. At small deformations, the fracture and the pull out of the fibers can be observed, while before the failure, the fracture of fibers is the dominant deformation process. In the case of talc PVE hybrids, no signals was detected at small deformations. Before the failure, similarly to the carbon fiber composites, the fracture of the PVA fibers gives signals. As we have seen before, no significant difference was observed in the strength and impact resistance of carbon fiber PVA and talc PVE hybrid composites, but the mechanism of the failure are different, as we can see here and the next slide. Observation is also proved by the presence or even absence of acoustic emission signals. However, these different processes absorb almost the same amount of energy. So in order to identify the deformation processes occurring during the failure, images were taken of the tensile surface of the composite using a scanning electron microscope. Both carbon fiber PVA and talc PVE composite, it is visible the fracture and the pull out of the PVA fibers. In the case of carbon fiber composites, the fracture and pull out of the fibers can be seen, while in the case of talc reinforced composites, the bond of the talc and the plastic deformation of the matrix around the talc particles is visible. These local deformation processes consume more or less the same energy during the failure, as we saw that from the previous slides. I mentioned at the beginning of my presentation that our goal is to prepare composites that have both large impact resistance and stiffness. In the figure on the left, the impact resistance of traditional composites can be seen as a function of stiffness. Its visible large impact resistance could not be achieved with these composites. The figure on the right shows the results of the hybrid composite. The addition of the polymer fibers, outstanding impact resistance was achieved. The proper combination of stiffness and impact resistance has been achieved, and the results for talc PVE composites suggest that they could be a cost-effective alternative to the more expensive carbon fiber PVA and glass fiber PVA composites. We have found that sufficiently high impact resistance and stiffness can be achieved with different deformation mechanism during failure. I would like to thank you for your attention and have a good day. Bye.